Good day, professors. Today, my team and I will be presenting on our IoT project, Building Fire Monitoring and Evacuation System. The team consists of me, Pirina, Nicholas, Clement, Velion, and Jianjie. This will be our table of contents that we will be presenting on today. So starting from our problem statement, traditional approaches frequently result in packed exits, ineffective evacuation routes, and considerable communication issues during emergencies. Our concept takes a smarter approach, utilizing LoRa mesh networks, MQ2 smoke sensors, and DHT11 temperature and humidity sensors. Combined with the power of Node MCU and Raspberry Pi, we are presenting not just a solution, but a revolution in fire safety. This IoT solution improves occupant awareness, resulting in a safer, more informed evacuation process. Let's take a closer look at how IoT is helping to make buildings safer.
So with all these problems in consideration, here are our goals. Our approaches reconsiders fire safety procedures around three key aspects. The first is decentralization, whereby creating a system with no single point of failure, and we provide unrivaled reliability during emergencies. Secondly, speed and reliability are paramount with our system, enabling the timely and dependable transfer of critical information across the building. Third, we add real-time data capabilities, which provides immediate fire location and allows for rapid emergency action. These qualities offer a strong foundation for a revolutionary fire safety system. Building on our strong features, we see significant advantage in our approach to fire safety. Our approach enables efficient evacuation operation, allowing individuals to reach safety faster and in a more orderly manner than ever before. Detection accuracy has increased significantly, enabling for faster identification and localization of fire outbreaks within the building. Finally, our approach is intended to significantly improve incident response time, making emergency service more efficient and potentially saving more lives. These benefits constitute a significant step forward in ensuring the safety of building inhabitants during fire situations. As for our proposed solution, we have decided to create a fully connected LoRa mesh system with the following sensors attached to it: a smoke sensor to detect smoke from the fire, a temperature and humidity sensor to detect a spike in the temperature and humidity in the event of a fire, infrared sensors to count the amount of people, and a Node MCU to connect to the internet, whereby we can publish the sensor details via MQTT to our Flask web server, which is running on the Raspberry Pi. And this is what the user can expect to see with our implementation. The user can see the data, the sensor data on both the serial monitor or the Flask web application. In the event whereby the Wi-Fi goes down, the user can still see those sensor data being transmitted via the serial monitor.
So why do we choose LoRa? We chose LoRa as our main communication protocol because we want to leverage on LoRa's features, which are extended range, ability to penetrate through walls, its sub-GHz frequencies, which improves signal strength and reduces connection failures. These are all important in a fire detection system. However, in our endeavor to leverage LoRa's technology for effective sensor data transmission, particularly in critical scenarios like fire emergencies, we encounter a challenge inherent to LoRa's half-duplex nature. So basically, traditional LoRa nodes are typically designated as either transmitters or receivers. And due to this constraint, it poses a potential obstacle to the establishment of a resilient mesh network. So we recognize this limitation, and we devise a novel approach tailored to maximize the efficiency of a LoRa-based sensor network, while also mitigating the risk of a message overload and also consequent data loss. So rather than attempting to force a full mesh topology onto the current network, which could cause congestion and collisions between messages, we opted for a hybrid solution that optimizes the utilization of network resources. So this hybrid solution is a token-based protocol. So one of the foremost challenges we addressed was the inherent susceptibility of devices to failure amidst the chaos of a fire. And to mitigate these risks associated with simultaneous message transmissions, which often lead to collisions and subsequent data loss, we devised a token-based protocol. So basically, this protocol grants transmission rights, or TX mode, to nodes holding the token at any given time. And by ensuring that only one node can transmit data at a time, we effectively eliminate the potential for these message collisions, minimizing message loss, and also maximizing network efficiency. So central to our protocol's design, its ability to maintain a full mesh topology helps to foster resilience and reliability within the network. And through the token system, we uphold a dynamic yet also controlled environment, where the nodes can be able to seamlessly communicate with one another without encountering the pitfalls of congestion. So this approach not only optimizes the utilization of network resources, but also bolsters the network's robustness, crucial for real-time monitoring resources in critical events like fires.
So we'll be talking more about how to set up the IoT devices. So this diagram illustrates the setup for establishing connection to each sensor as well as to the UNO and the Node MCU. Then you can refer to this diagram when setting it up. So each UNO and LoRa shield must have a unique identification within the mesh network. Therefore, prior to flashing the code, you must modify the node ID according to the desired number assignment within the mesh. Then this ensures that each address is distinct and avoids conflict. You can also increase or decrease the number of nodes with the max node variable. So to ensure proper functionality of all Wi-Fi connected devices, they must be connected to the same internet network. Therefore, it's crucial to configure the Wi-Fi details in the wi-fi.ini file to match the network connected to both the Flask and Raspberry Pi, which they should also be on the same internet network as well. Before initiating the web deployment, ensure that Mosquito is running on Raspberry Pi as the broker. Then confirm that the Raspberry Pi, server device, and node MCU are all connected to the same network. Additionally, verify that the broker IP address in both the node MCU and Flask web server matches the IP address of the Raspberry Pi to establish a successful connection. So we'll be now showing the demo of our project.
So I'll now conclude our project. So essentially, the benefits of our project is that we actually created a LoRa mesh system without the need of a central gateway. So this has allowed us to have long distance communication, energy efficient system, and lastly, very high message reliability. So along the way, here are some discoveries and limitations that we have identified. So this includes power affecting the behavior of the LoRa devices, a trade-off between latency and reliability based on the implemented token-based system, as nodes now have to wait for their turn to transmit data. Unable to work with the IR or HC SR501 PIR sensor accurately. And lastly, that the LoRa is unable to send and receive at the same time because of its half-duplex nature that we have implemented a token-based system to overcome. So here are some alternative use cases that can be used with our project. Firstly, environmental monitoring, where you can monitor air quality, temperature, and air pollution. Secondly, a smart parking system where you can detect lots occupancy and also relay the information to a mobile device. That'll be all. Thank you.